everyone. I'd like to welcome you all to Spex CertaPrep's webinar, Identification, Preparation, and Analysis of Imported Plastic Children Toys for Restricted Elements. My name is Amy Williams, and I'm the Marketing Manager here at Spex CertaPrep, and I'll be moderating the presentation today. Before we begin, I just want to get a few housekeeping tips out of the way. Everyone in attendance will receive emails with the presentation slides, and then also an email with a link to the webinar recording on our YouTube channel, and that will probably go out next week. The slides will go out today or tomorrow morning, and the recording will go out next week. If you have any questions during the presentation, please type them in the question box on your screen, and we'll answer them during the Q&A session after the presentation. I'd like to introduce our speaker today, Patricia Atkins. Patricia is the Products Application Specialist for Spex CertaPrep, and I'm sure that a lot of you will recognize her as a regular from a number of our past webinars and research projects, including the trace elements in lipstick, the chemistry of wine and BPA, and phthalates in plastic toys. Patty?
Thank you very much, and I would like to welcome everyone to our presentation this morning. If you are going to be at ASMS, we also welcome you to stop by our poster. We'll be having a poster on this topic at this upcoming ASMS meeting in Baltimore. I'd like to get started just talking a little bit about the toy industry and its importance to study different toys because of their impact on our economy as well as the impact on our children. First of all, the toy market worldwide is a very big business of $84 billion a year, and the U.S. is the single largest importer of children's toys, from $22 to $35 billion a year. More than 75% of the U.S. toys here are actually produced in China, and these Chinese products, toys and other Chinese products included, account for more than 60% of all product recalls. China also supplies more than 81% of counterfeit goods seized by customs, like our friend the doll here. What's amazing, though, is that only a very small percentage of all of these toys that come into the U.S. are actually rejected for exceeding limits. And from 2010 to 2014, there are on the CPSC website 14 toy recalls specifically for chemicals and/or lead. The toys themselves are composed of many different types of polymers, from an ABS type of plastic, which is a hard material that's usually molded. It's most commonly seen in things like Legos or building bricks, to softer plastics like PVC, or some durable plastics like polyethylene. You could have a toy like the car here, which is composed of many different types of polymers all put together. What's of concern is these toys can contain a lot of hazardous materials, as well as being physically hazardous to a child. These toys can contain things like heavy metals, phthalates, and bisphenol A. And these restricted compounds and elements could be found almost anywhere in the toy. The paint on the stickers, the paint applied to the plastics themselves, the polymer that the toy is made out of, and if the toy contains an electronic component, then you have the RoHS directives governing the different heavy metals in electronic components. Mostly when we think of heavy metal exposure for children in toys, we hear about lead. Lead has been famous for being a case of poisoning in children, mostly because lead poisoning is associated with paint. Now, lead paint was banned for home use in 1978, but 25% of U.S. homes with children be used to stabilize. Lead paint, especially lead-2 chromate and chrome yellow, and lead-2 carbonate and white lead, are primary formulations of lead in paint. Another potential source of heavy metal contamination for children is cadmium. Cadmium is the byproduct of zinc smelting, but it's also used as a PVC stabilizer and a color. used as Paris green colorant, Chrome 6, which is found in chemically treated wood, steel manufacture, and other colorants. And there's antimony, which is a catalyst for polyethylene terephthalate and flame retardants. Finally, there is barium that's used in different paints. In the ES and in Europe, there are regulations regarding lead in paint layers, metal content in children's toys, total lead levels, the migration of lead and other elements in and from children's toys. And the limits are very similar. The most notable limits are the limits for lead, which are about 90 micrograms or milligrams per kilogram, excuse me. There are two types of ways to study the lead and other content of children's toys and paint. There is a migration, which is tested by leaching the material in a matrix that simulates a hydrochloric acid stomach contents. And then there's the total amount, where the total amount of a banned element is measured in a total toy weight. Over the last few years, the levels of acceptable lead have dropped from 300 ppm to 90 ppm. For our study, we had 26 toys from dollar or discount stores. We separated them into their component parts, which gave us over 65 different samples. We tried to choose items that were designated for oral contact, meaning that they were designed to be placed in the mouth. Things like our funny teeth, our whistles, our snorkel. Then there are items that are suggested to have high probability of oral contact or mouthing by small children. These are items that, within reason, would be placed in a child's mouth during play. Things like our rubber duck, our doll, and our toy soldiers. The toys were disassembled into their different components of different polymers. So our truck here, the wheels were taken off, the silver seats inside were separated, the stickers were removed, and when it was possible, we tried to separate the paint from the underlying polymer and use that as a separate sample. We also did a homogeneous grinding of parts of the toy using our Spex sample prep freezer mill and liquid nitrogen. We cut 2.5 grams of plastic into about 5mm pieces and then ground it to a fine powder using liquid nitrogen and cycles of pre-cooling and cooling. What this gave us was a fairly homogeneous powder, and you can see that parts of our rubber duck, it was a nice fine powder. Our whistle and our teeth also give us a very fine powder. Now, we had used these toys in a previous study that we referenced a year or so ago, where we did organic components on these toys. And for that study, we were following a CPSC method, which the toys were suggested to be cut into under 5mm pieces. And we were not sure if the actual size of the particles was going to greatly affect our extraction at that time. So we did a little study and we extracted them 5mm pieces, 2mm pieces, and some powder. And you can see we got a lot more extract from that powder than we did from the larger chunk pieces. When it comes to sample digestion, a fine powder is a little easier to digest, or at least uniformly digest, than compared to a large 5mm or 2mm piece. Our next step was to try to decide what type of polymers that these different toys fell into. This is an identification chart of the most common polymers in use with their recycling codes. And we have things like the polyethylene terephthalate, which is most commonly known as soft drink bottles. And the primary dangers from PET are acetaldehyde and antimony, which are used or byproducts of the manufacture. Then you have your polyethylenes, your high density and your low density polyethylene, which we know as being milk jugs, bottles, shopping bags, but they're also components of many toys. Now, overall, the literature, there's not a huge amount of phthalates or other additives in these polyethylene materials. So they're considered to be a little bit cleaner on the scale of, at least in organics, the cleaner for some of these potentially dangerous elements and compounds. We also have PVC, which is, on the other hand, notoriously dirty for organic compounds. This is pipe, shower curtains, especially toys that are considered to be soft toys. And they are loaded with phthalates, bisphenol A, and potentially heavy metals. Some of the other polymers that are not quite as common polystyrene, polycarbonate, ABS, which, as I've mentioned before, is most famously known because they're a component of Legos. And they each have their different dangers or hazards. So for us, the first step in the identification was to see if there was any recycling marks on our toys, and unfortunately there wasn't. That left us with a bit of debate of how we go about identifying our different toys. And there are a lot of analytical tools that can be used to identify plastics, FTIR, IR. Not having one of those instruments in our laboratory, we decided to go kind of old school, and we compiled a chart of the different physical and chemical characteristics of each of the different polymers. And we then went about testing each of these different physical and chemical criteria and narrowing down our choices to what type of polymers they were. Overall, it came down to a spreadsheet or a flow chart that looked like this. And don't worry if you can't read all the fine print. I'm going to go into a little bit more detail, but this is the overall scheme of things. The blue boxes were density tests, where we tested the plastic against a certain density standard. The pink triangles or the pink diamonds were solubility tests, where we tried to dissolve our plastics in some different types of solvents to see if they were soluble or not. And the yellow triangle at the bottom was a flame test, where we actually set fire to some of the samples using a copper wire and observed what type of residue, smoke, or flame color it produced. So like I said, the first step in this process was a density test, and the easiest one was a density test against water, which was able to separate our plastics into whether they were the lighter plastics like the polyethylenes, the polypropylenes, or if they were the heavier plastics like the PVC, the polystyrene, and the polycarbonates. From that point, when we took those plastics and we tried some solubility tests, such as in DCM, that was able to divide out the polyethylenes, which are very insoluble in almost all solvents, to something like an ABS or a polypropylene, which was soluble in DCM. Then we did more density checks to find out if it was a low density or a high density polyethylene, or if it was a polypropylene or an ABS plastic. Finally, when we were looking at the other side, some of the heavier plastics, again, we did some density checks to bring it down to the last level, where we did the flame test to prove if it was PVC or not, because PVC burns with a green flame. So our sample identification was as follows. Most of our toys were polyethylene toys, either LDP or HDPE toys, and PVC. We had a few of the other plastics represented, some polycarbonate, a few polypropylene, one ABS toy, silicone, and some poly cloth. We were not sure of the composition, but it was some sort of cloth material, probably a polymer based. Since notoriously PVC toys are very dirty with organic contaminants like phthalates, we thought this would be the best place to start looking for heavy metal contaminants. So some of our PVC toys turned out to be some of these dinosaur figures, our friend the rubber duck, the teeth, and the snorkel. The teeth and the snorkel were of particular interest because they're meant to be put in the mouth. We also had some cartoon figures that we've blurred out the identities to protect the innocent. If you're interested in some of our previous work on the organics, like phthalates and bisphenol A in toys, you're more than welcome to look at our webinar, the sample preparation and extraction and analysis of imported children's toys for phthalates and bisphenol A. I'm going to give you a little snapshot because this shows you why we decided to pick these PVC toys. During that experiment, we were basically following the regulations from around the world for the US and the EU and Japan when it came to 6 banned or restricted phthalates, the DEHP through the DNOP. In the US, we're allowed up to 0.1% of each of these phthalates, but especially ones with oral contact, things in the pink, those are the ones that we have 0.1% for each of those. In the EU and Japan, you're up to 0.1 combined for the different groupings of phthalates. Here's a snapshot of what we found in our PVC toys. If you see the orange dotted line, that's the US limit, that 0.6 total. And most of our toys, barring about 4 of them, of our PVC toys, exceeded the limit that would be allowed for the U.S. to be sold because of these restricted phthalates. Most troubling is that pink snorkel on the end, which is way above the U.S. limit and is actually meant to be put in the mouth. The purple dotted line is the EU limit, and this is the lower limit, that 0.1% for total. So overall, what we found is we found several different phthalates, but the DEHP was actually our most detected phthalate, and it was in 15 out of 17 of our toys. And 12 out of 17 of these PVC toys would have exceeded the CPSC limit of 0.1% and would not have been allowed to be sold here in the U.S. So we decided that these would be our first contestants in testing our metal content. Our first experiment was a digestion experiment. We used our CEM Mars 5 microwave with easy prep vessels. 0.1 grams a sample with 10 mils of nitric acid, and a pretty standard ramped temperature to 210 degrees Celsius with a 15-minute hold. What we did find that some of our PVC samples, not all of them, but some of our PVC toy samples did not digest completely, despite having tried to digest them several times. And this could be because there are certain additives that that prohibited the complete digestion, or maybe the additive themselves didn't really digest. We should have maybe brought the temperature up in order to digest that additive. But not knowing what some of these potential plasticizer additives were, we did have some incomplete digestions. And we handled that by a very normal way of taking our sample residue and filtering it and then drying it. For our standards, of course, we used our CLMS suite of standards for ICP-MS and our ROWE standard. We used high purity, very high purity nitric acid and high purity HCl to eliminate any potential contaminants. Our study was done using an Agilent ICP-MS 7700 with the cyclonic spray chamber and the Meinhardt nebulizer. We did perform a collision mode with helium on our samples to try to avoid some of the polyatomic interferences. We were able to monitor a large suite of elements, but we really focused on the quantitation of the restricted elements. And you can see we did have a large suite that we were able to look at, and most of the time we were looking at some of these elements for potential interferences. So our first digestion, this is a snapshot of our first digestion. It was a little anticlimactic, to be honest. We were expecting huge amounts of lead. We had read papers, we had done background research. We expected large amounts of lead in our samples. But what we found was that the lead limits were definitely way below what was allowed. We did try to find some paint samples, and it's very difficult to sometimes isolate just the paint sample from the polymer underneath. And in many cases, these toys had been used for another study earlier, and by the time the metal study came around, there might not have been a lot of paint in some of the areas of the toy to isolate a large enough sample to give us an analytical result. Two results that did catch our eye, though, were a large amount of barium, which was found in our duck and our donkey samples, and some antimony, which was found in our snorkel. Now, the antimony we found at 40 milligrams per kilogram is under the limit of 60 milligrams per kilogram, but for having a toy that's being placed in the mouth, that's a pretty high result for a toy that is meant to go in a child's mouth and have sustained contact with their mouth. So then we decided, okay, we didn't quite see what we thought we were going to see, so let's try a different tack to it, and we chose a migration method. We also expanded to look at some of the other types of polymers, some of the other toys. We chose some HDPE and LDPE toys, our action figures, some of our toy car parts, and our baby sippy cups. We also looked at the paper stickers from the car, this doll's dress, the flute with the medallion, which is also meant to be put in the mouth, and we decided to test our friend the rubber duck, who was basically one of the culprits in our organic study. For this study, we based it on the EN71 migration extraction method. We did use our CEM Mars microwave system again with our express vessels. 1 gram of sample and 10 mils of 1 millimolar HCl to simulate a gastric fluid environment in a child's stomach. It was run at 37 degrees with stirring for 2 hours in darkness. One of the problems that we found came down to the calculation of how you interpret these results. Because the samples are extracted or migrating from the toy into the matrix, you can calculate it in 2 ways. Now, there are instrument app notes and different app notes from vendors that suggest that they were following a filtration dry weight method where they took the sample after it had been extracted and they filtered it and then took that filtrate, dried it out, and reweighed it. And that became the basis of their calculation. For us, that was a very, very small amount. The amount that actually extracts into the matrix was about 10 milligrams, a very tiny amount. Now, there is potentially the benefit because you're seeing the actual portion that migrates into the matrix, but anytime you have to dry and reweigh your samples, you exponentially increase your error. The more common way of looking at it, and the way prescribed by the EU, is looking at the total weight of the sample, or the total weight of the plastic that you put into your extract. For that, that was 1 gram. This overall takes your results, though, and spreads them across that 1 gram sample. If we take a look at the dry weight, that very small, tiny amount, you can see that almost all the toys actually exceeded the barium limit, the chromium limit. Quite a few of them exceeded the lead limit, and some of them also exceeded the antimony limit by factors. I'm not entirely sure this is an accurate representation of what the concentration would actually be in a child's system. If you look at the total weight way of calculating it, then most of the results do fit within the limit allowed. The only exceptions are for barium, where our friend the duck again became the villain of our story with 5,000 milligrams per kilogram of barium, and the silver seats in that little car were at 1,000, right, just at the limit. We also had antimony, which was higher than almost all the other samples we tested in the doll's dress. Now, it did not exceed the limit for antimony, but it was much higher, order of magnitude higher than some of our samples. Now with 2 studies under our belt, and we said, okay, let's do a follow-up, and we'll do a second digestion of some of the more interesting toys from the first 2 runs. And we did our cars, we did our doll's dress, and a few of the other items. What we did find is when we did the second digestion, those barium levels did fall below the limits, but the antimony level in that doll's dress went way up. So the antimony was there in the sample, but was not actually migrating into the extraction. So the antimony in the doll's dress was 301. If we look at a comparison of the digestion and the migration results, here we have our silver car seats. For the digestion, all of the results actually do fall under the limits, but the migration shows that the barium actually migrates and up to the limit for those silver car seats. Our friend the duck, the barium levels in the migration seem to be very high, but all the rest of the results fall within limits. It seemed that the higher barium levels were found in our migration studies. But things like the arsenic were only slightly higher in our migration studies over the digestion, and things like cadmium, chromium, and mercury were at very similar levels, no matter whether it was a migration or a digestion study. The antimony and lead levels, though, were clearly higher in the digestion rather than in the migration. Here's our doll's dress, where we can see that antimony, which was a little high in the migration but was very high in the digestion. And in our migration study, the barium would exceed the limit, but the digestion was definitely under the limit. So some of the challenges that we found with analyzing toys for metals. There were digestion challenges. It's very difficult to predict whether all the polymers are going to dissolve, especially when the polymers are from different sources or contain different additives, which sometimes changes the chemical composition and makes it more difficult to digest. Also, determining the residual weight of any undigested material can be a problem and add a source of error to the calculations. And it is very, very difficult sometimes to separate the polymer from the paint for analysis. It was difficult when scraping the paint off not to get the underlying polymer and therefore then add polymer into your total sample weight. And as I said before, since we had a limited amount of paint on our sample, sometimes trying to collect enough paint to get a result was a difficult process. For the migration, you have different cited ways of calculating the analytical results. And we found that not all elements will actually migrate at the same rate when compared to digestion. And then there's how do you test your toy? Do you do surface coating testings? Do you look at the total toy amounts? Or do you do a migration study? There's also the problem that there's not a lot of matrix match standards for paint and different toy polymers in order for you to really understand what your recovery is for either an extraction or digestion. In conclusion, the lead levels that we expected to find very high in these toys were all within specifications despite whatever method we used, the digestion of the total weight. Now, if we had been able to isolate more of the paint samples, or we had a bigger sample batch to collect a larger sample size of the different paints, that might have changed. But as the toys were ground homogeneously in some cases, or we did try to isolate a small amount, that just wasn't enough in order for us to find the lead in our extract or our digest. It was not possible necessarily to see the lead in those paints. Our dry weight migration methods had results far above all the limits for almost all the targeted elements, and I have some suspicion that this is probably not the best way of trying to calculate this type of information. The highest elements we did find overall were barium and antimony, with barium being in our friend the rubber duck and in the silver seats of the car. Antimony being in the dress, and a little bit concerning was also in the snorkel. The total weight and the digestion methods were comparable for several elements, including the cadmium, the chromium, and the mercury. But what we did find was the antimony levels were often highest in the digestions, while barium seemed to really migrate quite well into the extracts. So for the migration studies, barium was the highest. I would like to thank all the Spex sample prep staff who helped me grind our toys with our freezer mill, and all our Spex CertiPrep chemists and analysts who helped do the ICP-MS analysis and helped me with my samples. And I think we'll take time for a few questions.
Yep, that's right, Patty. Thank you very much. We have some questions from the audience, and so we'll go through a few of them now. Okay?
Okay.
So the first question we have is, what country were the toys in the study from?
We got toys from dollar stores, and it was not by design but by accident that all of the toys that we picked up seemed to be from China. I don't know whether it's that just most of the products in those stores are from China, but all of the products were marked made in China that we looked at.
Okay, and did we test any brand name or U.S.-based toys?
As far as I know, these were all just cheaper dollar store toys, and we purposely did not look at some of the more expensive toys. First of all, trying to get a budget to get $20, $30, or $40 toys, 20 or 30 of them at a time, would have been cost prohibitive for a small study like this. And in honesty, the dollar store toys have a large access to the public, so we wanted to see, what was passing through a lot of people's hands. I know, being the mother of a small child, it's very easy when you're going into a discount store to pick them up a cheap toy and just hand it to them, then buy something off a shelf and pay 5 times the price. So we really just focused on the cheaper dollar store toys.
Are you planning on following up with any of the brand name or U.S. toys?
There's been a lot in the news about different brand name toys. The industry for themselves does try to police itself. They are actively engaged in a lot of toy testing to make sure that they are compliant. My concern was that these smaller toys, which do kind of pass under the radar, were the ones that had the biggest potential to expose children to some of these dangerous elements. So at this time, we do not have any plans to follow up with some larger toys, but you can go to most of the major toy manufacturers' websites, and you can see if they've had any toy recalls. They're pretty good about keeping up with their recalls and their different warnings.
Okay. And is it possible that the results could have changed by analyzing the chunk components of the toys rather than grinding them?
Oh, absolutely. We chose to look mostly at the ground samples because, as I said before, this was a two-part study. The toys were first used in an organic study where the paint is not as much of a concern in the sample itself. So the toys, for the most part, not all of it, but for the most part, were ground. So that made that accessible for the second part of the study. In some cases, also making is an analytical choice in the laboratory for a toy testing laboratory or consumer testing laboratory. Which part of the toys do you sample? Do you sample the part with the red paint? Do you sample the part with the black paint? Do you try to composite them all together? Do you try to separate it out? And as I said before, my hat's off to any laboratory that has to separate paint from toys because it is a very tedious process and it can be very time consuming and sometimes you definitely, after hours of work, don't get enough samples to really give you a good analytical result.
Okay, and we have time for one more question, which is one that I can help answer. And the question is it possible to get a copy of the Phthalate slides presentation? And yes, it is possible to get a copy of that. And what I'm going to be doing is sending all of the registrants for today's webinar a copy of all the slides of this presentation and the previous presentation as well. And then in a week or so, we'll have the webinar on our YouTube channel, and I will also send all of the registrants a link to that as well. But I want to thank everybody for coming to the presentation today. And I also want to point out that Spex Certiprep is glad to be celebrating our 60th anniversary this year. And with this anniversary, we do have a brand new catalog available. It's our 2014-2015 inorganic and organic catalog, and it's available online. And also, if you would like to receive a hard copy of this catalog, you can please email me, and my email is actually on the previous slide here at awilliams@spex.com, and I will be glad to send you a copy of the catalog. But again, thank you very much for attending the webinar today, and we hope you found it informative and interesting.